Okay, so for this first video, or I'm sorry, not for this first video, but for this derivatives of trig functions video, we're basically going to find out how to do the derivatives of the six trig functions. I'm going to prove like one or two of them and then just kind of, accept that the rest of them will be done in a similar fashion. I haven't proved some of them in a long time. The main ones I prove is either the sine function, the cosine, and the tangent. I don't normally do a bunch of the rest of them, but pretty much once you have the sine and cosine, you can kind of do everything else. So I'm just going to show you guys how to prove the sine function. So let me just make sure. Okay, so let's see here. Let's say that we have f of x is equal to the sine of x, okay? And we want to find f prime of x. So what we're going to do is we're going to need two things. So we need, for some of these proofs, we're going to need the limit as h approaches 0 of sine of h over h is equal to 1. And we also have the limit as h approaches 0 of cosine of h minus 1 all over h equals 0. Okay, so these two limits, you could go through and build a table and try to find the limits for these. Sine of h, and this is in h. Okay, so these two limits are things we're going to use throughout this section, and they'll be used in finding the derivative of the sine function. So the first thing I'm going to do is I'm going to rewrite our limit definition of derivative. So the limit as h approaches 0 of sine of x plus h minus sine x all over h. Okay, now we can use our trig. You guys remember whenever you have the sum or difference inside of the argument of a trig function, what we can do is we can take the limit as h approaches 0, and I'm going to use our angle addition formula of sine of x cosine of h minus, let's do plus cosine of x sine of h, all minus sine of x all over h. So I'm going to regroup these, and I'm going to do sine of x cosine of h minus sine of x, and then I'm going to move the cosine of x sine of h over to the side, and it's all still divided by h. Okay, so now similar to when we prove the product rule, I'm going to do some factoring, okay, and reorganizing of the limit. So I'm going to factor out the sine of x. So I'm going to be left with the limit of the cosine of h minus 1 times the sine of x. You know what, let me write it in the front. That'll be better. All over h plus the cosine of x sine h all over h. You know what I like? Because I know that I'm looking to try to find this formula in there, I think what I'm going to do right here is I'm going to write it as sine h over h. Okay, and then this whole thing I'm taking the limit of. Now we know that I can split the limit. So this will become the limit as h approaches 0. And now what I'm going to do is I'm going to take the limit of each one of these separately. Okay, or in fact, actually, if I want, I could move the sine of x, because remember, this is as h approaches 0. It has nothing to do with the sine of x. So I'm going to take the sine of x out of the limit. And this will be the cosine of h minus 1 all over h. Plus, now what we can do is we can do the cosine of x. Cosine of x as the limit as h approaches 0 of sine h over h. Okay, so all I did is I took this and moved it outside of the limit, right? And then I took this and moved it outside of the limit, okay, which is right here, okay? And then I took the limit of each one of these separately, okay? Which is one of our limit properties. So now what I can do is I can use the fact that the limit as h approaches 0 of cosine of h minus 1 over h is equal to 0. So we go up here and we see that this is worth 0. So this would be times 0. And then this would be plus the cosine of x, and we know that this limit is worth 1. So we end up with cosine of x. So what this means is that the derivative was cosine of x. So now what I can do is I can go up here and I can put this in my table, cosine of x. Now, I'm not going to go through and prove the cosine of x one, but the cosine of x would be negative sine x, and you would do it in a similar fashion. Okay. Now, if you wanted to do the tangent one, you could, and you probably could get away with not even using the limits, because now we know sine and cosine. So if I said that f of x was worth tangent of x, then f prime of x, well, you know what? I'll do this. That means that f of x is worth sine x over cosine x. Remember, that's just a rewrite of tangent. So if I want f prime, I just do the quotient rule. And the quotient rule says the derivative of the numerator, which would be cosine x, right? I'm just looking up here. Right here, the derivative of sine is cosine. Rewrite the denominator minus rewrite the numerator. And what's the derivative of the denominator? Negative sine x. And once again, I'm just using the fact that the cosine of x is worth negative sine x. Okay. So this would be cosine squared x plus sine squared x. But, oh, hold on. Sorry, I forgot. I was wondering what was about to happen here. And then you have to divide this by the denominator, which is cosine squared x. Now this will become cosine squared x plus sine squared x divided by the denominator squared, cosine squared x. So then this becomes 1 over cosine squared x, but we know that 1 over cosine squared is the same as secant squared x. So I come over here and I now know that this is secant squared x, okay? So then I'm not going to go through and prove all these, but it would be done in similar fashions for a lot of these now that you know sine and cosine. Cosecant would be negative cosecant x cotan x. Secant would be secant x tan x. And then this would be negative cosecant squared x. So something to notice is the fact that we have all of the ones that start with the letter C, cosine, cosecant, cotan, they all have negatives. Okay, that's just something to keep in mind for memorization purposes. Again, even though if you're taking this course online with me, you obviously don't have to memorize them because you would have open notes, but you really want to memorize these 6. It's very important that you know these because it'll help you. It's kind of like not knowing your times tables when you do math. Yeah, you could still do math, but everything you're slower at everything else and it takes you a long time. These are definitely ones you should memorize. You should make flashcards for them just so you know them off the top of your head. Okay, so let's move on here. Okay, so we have this one. So now what we're going to do is let's try to do a few problems. So example problems. Let's take a look at some. Okay, so why don't you guys try to find the derivative of these? So let's say g of t is equal to t squared cotangent of t. Okay, and let's say we have f of theta. F of theta is worth sine theta plus cosine theta all over cosine theta. Okay, so take a minute, pause the video, and give these two a shot and see if you can use now your trig functions to work with these problems. Okay. Okay, so hopefully you guys have unpaused the video and you got both of these done now. So this is obviously we need the product rule, right? Okay, so what we're going to do is we're going to say g prime of t. Now the derivative of the first is 2t. Rewrite the second. Oops. Cotan t plus rewrite the first. And again, I know the book does it opposite. This is just how I learned it. And then the derivative of cotangent, if we go back up here and look, what's the derivative of cotangent? It's negative cosecant squared. So in this case, it will be times negative cosecant t squared. Okay, not the t itself squared, but the cosecant. So let's do a little cleanup on this. So let me see if there's any factoring we can do. Let's see here. We have 2t times, now cotangent is cosine of t over sine of t plus, let's do the minus t squared over, now cosecant is really 1 over sine. So I don't know if there's any cleanup. So that's technically our answer. This is technically our derivative. Let's see if we can clean this up at all. So that's one of the things in the trig homework you're going to have to do, is they're going to always want you to simplify. So let's see if we can do that. I think I could make common denominators. I don't see that helping. I could give this a sine t, and I can make common denominators, but that's not going to help at all. So what I'm going to do instead is I'm just going to say, let's not do that. I'm just going to factor out a t. So this will become t times 2 cotangent of t minus t cosecant squared t. I think that's the best it's going to get because I don't see it simplifying very well. Now, if they specifically ask you to convert everything to sines and cosines, then you would have to do something like that. But if they don't say, then I feel like that's going to be a good enough answer. Okay, you're always, by the way, on the lookout for sine squared theta plus cosine squared theta equals 1 or some variation of the Pythagorean identity. Because a lot of problems can clean up if you get sine squared plus cosine squared. All right, so this one, hopefully you thought first quotient rule, because this is division. So you may have thought quotient rule, and you're like, okay, I got the quotient rule. But I'm going to tell you that the quotient rule will work, but it's slow. I'm just going to use algebra first, or trig in this case. So what I'm going to do is I'm going to split it. This divided by this and this divided by this. That's legal. So then I get f of theta. I'm not even doing a derivative. This is just a rewrite. Sine theta over cosine theta plus cosine theta over cosine theta. So now this is actually tangent theta plus 1. Now that's really easy to take the derivative of now, right? So that's why you use your algebra first. We go over here and we say the tangent of theta. The derivative of it would be secant squared. So this is secant squared theta. And what's the derivative of 1? 0. So that's my answer. So by using algebra first, I didn't have to do the quotient rule. Not saying this always works, but this is something you always want to be on the lookout for to simplify things for yourself. Okay. All right, so now let's take a look at, so it says determine the, sorry you guys, I'm being attacked by my cat right now. Determine the points between 0 and 2 pi, where y equals cosine of x plus square root of 3 sine x has horizontal tangents. Now, what does a horizontal tangent line mean? So let's say that you have a graph like this, right? where are the horizontal tangents? Well, the horizontal tangents would be right here and right here, right? That's where it has horizontal tangent lines. So what is the slope at a horizontal tangent line? What is the slope of those lines? Think about that, right? It has a slope of 0, right? So those lines have 0 slopes. So, and the derivative, remember, recall, the derivative represents the slope of the tangent line. So whenever they talk about the slope of the tangent line, they're talking about the derivative. Whenever they're talking about the derivative, they're talking about the slope of the tangent line. They're very similar in that sense. So that means if they want to know where it has horizontal tangents, I need to find the derivative and set it equal to 0. So I'm going to find y prime is equal to, now the derivative of cosine is negative sine from our little table up top, plus square root of 3 times the derivative of sine is cosine of x, okay? So what we're going to do is we're going to say negative sine x plus square root 3 cosine x equals 0, okay? So let's see here. I guess I could move the sine x over to the other side. So I'd have square root of 3 cosine x equals sine x. I just added it over. Okay, and then I could divide both sides by cosine of x. Cosine of x. So then that means that we have the square root of 3 is equal to sine over cosine is just tangent x. Okay, so what we could do is we could then take out our calculator. Sorry about that. Thought I had it open already. Okay, so we could do second function arctan, and then it could be second function square root 3. Okay, so what if we wanted it in degrees, right? So we could go into mode. Right now it's in radians, so let's go to degrees. We're pretty sure we have the idea of where it's at, but let's just double check. Second arctan of second function square root 3. And we get 60 degrees, okay? So what that means is that if we have our unit circle, once again, right here at 60 degrees, we know, oops, that's 45-ish. Let's say right here at 60, we know that 60 degrees, or pi thirds, what am I doing? Okay, pi over 3, that has measurements for its x and y coordinates of, let me see, that would be 1/2 comma square root 3 over 2, right? Okay, so then that means, remember, tangent is the y over the x, so that would be square root 3 over 2 divided by 1/2, which equals square root 3. So that's basically what that's saying there, is that we have 60 degrees or pi thirds. I'm going to use pi thirds, so x equals pi thirds. Okay, but is there another location where we get a positive square root of 3? Well, look right here. If we just go straight another 180 degrees from there, or another pi from there, we're going to have the same measurements here, but they're both going to be negative. So this is going to be negative 1/2 comma negative square root 3 over 2. So I could also do negative square root 3 over 2 divided by negative 1/2, and that would equal positive square root 3. So that means another possible answer would be whatever pi thirds is. So I'm going to do pi thirds plus a pi. So that would be what? Well, I mean, I know the degree measurement. So this would be 4 pi thirds, right? So we get 4 pi thirds. But you could also just think of it this way. You could say, well, from here to here is pi. From here to here is pi. And then if we add another third, that would be 4 pi thirds, right? Or 3 pi thirds plus a pi thirds is 4 pi thirds. So these are the two locations where we have horizontal tangents, okay, for this from 0 to 2 pi, okay? And there won't be another location because you'll end up getting positive or negative values, all right? So let me take a minute. To do another problem. Oh, there's some homework problems I wanted to talk to you about as well. So we're going to return to limits real quick. Okay, and again, we're going to use the limit as h approaches 0 of sine of h over h. And the limit as h approaches 0 of cosine of h minus 1 all over h equals, oops, this equals 1, and this equals 0. Okay, so we're going to use these. I think I seem to, a lot of the problems I end up picking do this. I don't use the other one as often, but let's just kind of go through a few of these. All right, so we have find the limit as x approaches 0 of sine 3x over 5x, okay? Now, the thing is, the goal that we're looking for is we're trying to somehow rewrite these, and you don't have to worry about the h, it could be anything. But the thing we really want to focus on is whatever this argument is, it's divided by the same amount. And whatever that argument is divided by the same amount, that would equal 1. Or likewise, this argument has to also be in that denominator. So what we're going to do is we're going to try to manipulate these to end up with some of these limits. So we're taking for granted that we know this already, and we know this already. So we're counting that we know these two things, okay? So what we have to do is we have to somehow, in my mind, this is what I want. I want sine of 3x divided by 3x. If I could have that, then when I take the limit, then I know that I would get 1, right? That's what the property is saying, or not the property, but that's what this limit is telling us, if you could rewrite it like that. So what I'm going to do is I'm going to do whatever it takes to make that a 3x in the denominator. So I'm going to do the limit as x approaches 0 of sine 3x, right, divided by, so what I'm going to do now is I'm going to take and I'm going to write the 5 over here, 1 over 5. Okay, and then notice this x here, I'm going to leave it. Now I know I haven't done anything because what's x times 5? Well, that's just 5x. So I haven't done anything. It's still 5x. However, now that the x is there, what's the only thing I need? I need a 3 right here. So what I'm going to do is I'm going to put a 3 right here. Okay, now what is 3 over 3? Well, that's just 1. So this is totally legal. And I'm going to multiply and multiply, and 3 over 3 is 1, so I should not have changed the value. So now when I take this limit, now notice this is a constant and this is a constant. Constants are allowed to be pulled, when you're multiplying, they're allowed to be pulled out. So this is 3 over 5 outside of the limit. And this will become sine of 3x over 3x, right? So I know that this is actually 1, right? From right here. From this guy right here. I know that that's 1. So then we're left with 3/5 times 1, which is 3/5. And that's how you do these problems, is you try to make the argument match in the denominator. There's even a way you can do it with the numerator, because if two things are divided and you get 1, then that means those two things had to be the same. So it doesn't matter technically if they're in the numerator or the denominator. But that's just one way you can do some of these problems. I have another one that I want to do. Let me find it real quick. It's not in my notes. It's a problem I've done in the past that people kind of like the example of. So let's find that one real quick. Oh yeah, this one. So let's say we have the limit as x approaches 0 of, sure, sine 3x, let's do this, sine 3x all over 5x cubed minus 4x. Okay. So we can do something, oops, times 4x. Did I write it correctly? Yeah, 5x cubed minus 4x, okay? So the main thing we're trying to do now is we want to somehow develop one of these limits right here. We want them to come into play. Well, I have kind of a similar idea of sine of 3x. I need a 3x on the bottom, but unfortunately the denominator is kind of ugly. So what I'm going to do is I'm going to factor. And this one would become x times 5x squared minus 4. Let me see here, 5x squared. Yep. Okay. Now notice I could rewrite this if I wanted as the limit as x approaches 0 of sine 3x over x times 1 over 5x squared minus 4. That is legal to do because if I were to multiply these two back together, I would get this and it would be fine. But this means that I can now do this. I can now take and I can put a 3 here to match that and then put a 3 here just like last time. Again, this is coincidental that they both have 3x. It was just a coincidence. So limit as x approaches 0 of 3, oops, I can take the 3 outside, sine 3x all over 3x times, now I'm going to take the limit of this separately, limit as x approaches 0 of 1 over 5x squared minus 4. So now this will be 3 times, we know this limit is 1, times, now when I plug 0 in here, this becomes 5 times 0, which is 0 minus 4. So this would be 1 over 4, or negative 1/4. So then we end up with negative 3 over 4. Okay, so hopefully I didn't make any silly mistakes, but yeah, that's a problem I remember doing that a lot of students had trouble with in the past. And there's a few, I think there's like 3 or 4 homework problems on this. So give it your best shot. And, you know, you may have to use either one of these. I find that this one just appears more often. But, you know, you should be okay with both manipulating them to get it to happen. Okay, so let's move on. Okay, so what else do I have? Oh, I think that's it. That's it for this one. In the next video, the chain rule, we'll do more trigonometry in that one. But yeah, that's just kind of a practice on how to do trig functions with derivatives. The main thing is that you memorize these. So whenever you're asked to take a derivative of anything with sine, cosine, or tangent, or secant, cosecant, or cotan, you know how to do it. The next video on the chain rule, we'll be using this a lot more. So we'll get even more practice with trigonometry as well. Thanks for watching, you guys. I'm going to post this video for you.